So just to give you an example, last time I talked about how we want to make sure that the white matter surface that we have over here, it is topologically correct, right? That it is free of handles and cavities. So what also we can do is we can represent that white matter surface instead of a voxel grid. We can represent it as a surface made up of vertices and edges, and then we can pass that into a graph convolutional network. I think Paul, you are. Yeah. Sorry, I lost. What was I saying? Okay, so you can pass this mesh representation of white matter surface through a series of convolutional layers, but something called as graph convolution layers, which operates on graph representations. And then you can deform that input mesh to directly get a topologically correct output surface over here. So it goes from a white matter surface, which has topological defects, into a topologically correct white matter surface and also a PL surface, right? Which is the gray matter, white matter intersection. So these are a couple of papers which you can see again offline to give you an idea of how you can combine a voxel grid segmentation of your input and also its corresponding mesh representation together in a neural network to again give you better representations of segmentation and geometrically accurate objects, right? It is out of scope for today's topic, but just wanted to tell you that these papers are interesting to look at if you want to work with surface data. Okay, so we'll talk about recurrent neural networks and transformers. You already know CNNs pretty much by now. So you know that CNNs are mostly used for categorizing or understanding spatial data, such as images. And what about like sequential data, like our language or like sound waves, which has a sequential temporal stream to it? How can you represent this data and think about this data using neural networks? So we use recurrent neural networks for that. The other thing is that I'll talk about RNNs first, then I'll talk about how we can incorporate attention in RNNs. Then I'll talk about how what is transformers and how transformers is used in vision science, right? To set the stage, you might have already seen these things. E2, AlphaFold by Google DeepMind, OpenAI, GPT-3. These all networks, these have transformers as backbone architecture, right? And pretty much every architecture that people use these days have transformers, variant of transformers within them. Right. Some other examples, transformers are used in language processing, BERT and GPT-3, for biological sequences, AlphaFold, and also in computer vision in the form of vision transformers, right? Okay, so topics for today, about RNNs in the context of language modeling, that is translation of a sentence from one language to another language. Then we'll see how attention mechanisms are incorporated in recurrent neural networks. Then we will see what is the concept of transformer and how attention is incorporated in transformers. And while you go through these slides, think of the concepts that you have learned in lectures 1 and 2, of how attention from lecture number 1 is now directly, implicitly used in transformers, right? Then we'll briefly vision transformers. We'll look at some PyTorch code if we have time, of how easy these things are to code. And then I'll leave with a couple of or a few medical imaging papers which incorporate transformers, especially in the context of segmentation and registration. Right? We won't have time to discuss the papers, but I'll just put them as reference. Right. These are some slide credits beforehand. you already know this particular lecture series. And then most of the slides for this particular presentation are taken from this lecture and this blog post over here, the annotated transformer. Highly recommend reading this blog post in your free time. And then this particular YouTube tutorial talks about how you can build transformers from scratch in PyTorch. So sequence to sequence modeling, what is it basically? Sequence data that you have, you can pretty much represent that in recurrent neural network. So you all know that we have seen feed-forward neural networks or convolution neural networks to do some kind of classification or segmentation, right? You have an input X, you have your neural network F, which is basically a function F, which maps your input X to some output Y, right? So this could be used for classification, regression, or segmentation, right? Or even image registration. So over here, what is happening is that your input is just one of input image or a single text that you want to classify or segment, right? What if you have some kind of sequential data? That's where RNNs are used. And some of the examples of how RNNs can be used is in the following way. So you have this many-to-one application where you are given, let's say, a paragraph or a sentence, and you want to analyze the sentiment of that. That is whether it is sad, happy, or what have you, right? So you have many, which basically means a lot of text, and one is basically a single output, right? So you have a lot of different inputs and one output. Or you can also have an image captioning task, which is one-to-many, where your input is an image and your output is a caption describing what the image is, right? Or you can have a many-to-many task where your input is a paragraph or a sentence in one language, let's say French, and you want to translate that into English, right? So this is some of the use cases of RNNs, right? Or how you can think of sequence modeling applications. Today we'll focus upon this particular task. So think of this again. The working example over here is that you have an input in French, and you have a recurrent neural network, this black box thing, which we are going to tear apart, and your output will be the translated version of that sentence in English, right? So again, yeah. So this neural network, this RNN, will take one input at a time. So it will take, I don't know how to speak French, but think of, I'm saying this sentence in French. So I am a student. So it will first take, we can try. So anybody knows French? Well, je suis étude, whatever. 3 years of Cuban things. So I am a student. So it takes one word at a time, and then basically it outputs the translated word again, translated text one word at a time, right? And let's try to now decode this or try to understand what is going on behind this RNN step by step. So again, think of this RNN as nothing but an encoder-decoder, right? Just as you had in your unit architecture. In CNN, you had a unit which had your encoding block and then a decoding block, and there was a bottleneck features, right? So think of this encoder, which encodes the sentence. There is some context, which are like the bottleneck features, and then you have a decoder, which would decode your sentence into the other language, right? And as you can guess that each encoder and a decoder block would have a series of different components stacked one after another, just as you had in your CNN, right? So before that, now you know that we are going to input a text sentence and you're going to output another text sentence, right? But how do you represent this text input for the task of machine learning? Like, how do you want to build a neural network, but what is the kind of input that you're going to give to your neural network? Like, you can't directly give a text to your neural network, right? Because in images, you represent that as pixels. So how would you represent your word text in some kind of representation so that you can give it to the neural network? Anyone? How would you transform your text? Or like how would the machine think of text? Yeah. Yeah, exactly. Yeah. So anybody can like tell me what kind of vectors, any algorithm that you might know from your machine learning class? Any representation? Yeah. Yeah, yeah, exactly. Kind of, yeah, exactly. So think of your corpus of English words. Let's say you have 10,000 English words, and then you will assign every word some kind of number, right? Or some kind of vector. And that vector will be a representation for every word. And that is what you're gonna input, right? And for the output, you will expect the same kind of vectors, but in language. So before going into details, so these are some kind of different representations of your text in any language of your choice. You can look up offline. Uh, these are just different representations of every word in your vocabulary, right? And your vocabulary can come from any language. So for example, TF, IDF, basically you times a word is occurring in a given vocabulary, and it also focuses some attention on how rare a word is, right? Just to give you an intuition. Or like word to vec, again, as I was saying, a vocabulary can contain thousands of different words, and every word is given a vector in some 3D space, right? So the idea is that words which share the same sentiment are close together, and which are different in context are far apart. So for example, a shirt and a pant might be close together, whereas a cat and a table will be very far apart in your representation, right? So again, as I was saying, you just can't give words to your input network. You have to represent that into some kind of vector. This vector will be an input, and corresponding vector for each of the representations will be the output, right? So there is some vector for deep, which is this particular vector, and learning has this particular vector. So those are our input and output, right? So how, like one way of computing this is basically just to illustrate it here, you have vocabulary of the words in your training set, right? It could be thousands or 10,000s of different words or whatever. English language has the number of words. And every word, I just assign a simple number, 1, 2, 3, 4, right? So I index every word, and then I do one-hot embedding, which basically means that this is a long vector of, let's say, 1,000 words, the number of words that I have in my English dictionary. And if it's a cat, and I had assigned it 2, I will put a 1 in the place of where I had assigned it 2, right? And walk is n, so I'll go and create the vector of 1,000, and at the end position, I'll have 1, and everywhere else, I'll have a 0, right? So this way, you can create a sparse representation for every word in your vocabulary, right? And then you can normalize this and project into some vector space, and then get something like this embedding, right? And then this is a very vanilla way of doing it. No one really does it apart from intro to ML courses. Mostly these days, people learn these representations, and neural networks are used to learn these representations. And then once you have these representations learned, you can use it for some other task, right? So yeah, just to give you an idea of how things are done. So again, as I was saying, things which have similar meaning, or like which share sentiments, are happy and sad, are placed together. Animals are placed together, right? Yeah. Okay, so now I just want to translate my word from French to English, right? So the way it's gonna be this particular setting of many to many, where I'm gonna put my entire sequence into the neural network, and my output will also be the entire sequence, right? And every word in that sentence, I am a student, will be represented as an input, right? So I is an input, am, and student, these are different inputs, and we will just call them as time points for the sake of giving it some sequential notion. So think of this as three different words, x0, x1, x2, right? And your output over here will be the same word, but in a different language, right? And the way that we are going to think about it is that every word is going to be translated into the corresponding word in the other language using some function approximator, aka some neural network here, right? Okay, so the other thing to note over here is that when you're translating sentences, for people who are bilingual or more than 2-3 languages, you know that the word construction or the sentence structure is not the same, right? From if you're speaking one language and translating other language. So what is important over here is that you understand the whole context of a sentence, right? Because pronouns in some languages are at the end, in some languages, the articles at the front, and like, right? So really need to understand context of the entire sentence when you're translating from and different sentences. So what I'm trying to hint is a particular concept that we already saw in these set of lectures. Can someone tell me when you think of context, what you should think of? Yes. Yeah, but which I threw out in the lecture. Attention, right? You want to attend to different part of the sentence so that you understand the entire context, right? So let's think, let's look at this particular word of this particular sentence, right? I'm a student. So let's assume that this word is student, right? And you're translating this from language 1 to language 2. So, okay, I have a neural network which will translate my word student from one language to another language. But since I'm giving it as a sentence, I should also be able to see the entire context of the remaining words in that particular sentence, right? So the one way to do is that you can get context from this variable called hidden state, which basically captures all the information coming from the other part of the sentence, right? Does it make sense? So when I'm translating the final word, not only I'm looking at the current word, but I'm also looking all the information in the sentence before me. Right? So now let's just just look at this equation. Your input is xt, basically this guy. Your other input would be all the context information, all the hidden information from all the previous states, right? And these two inputs go into this neural network, and then you get some particular output, the translated word for that sentence, right? And then I just gave you an example for this last step, but nothing stops us from doing it for the previous steps as well. So somewhere, if it's a long sentence, somewhere in the middle, again, I have the input for that particular time step, information coming from all the hidden states, which captures information from all the previous words, and then it gives you some kind of output for that particular word, right? So these hidden states, right, which captures context for the previous words in the sentence. So just take a note of this particular cell. We will call this particular small component as a recurrent cell, because recurrence relation basically when you feed the output from the previous hidden states into right. So again, x of t and h of t go together to give you output y of t. Okay. And this is just again a pictorial representation of what is going on. Over here, I just showed you for one particular small sentence. Now think of this particular structure as a long sentence. Again, at every time step, you have input, you have hidden states coming from the previous step, you have your output, right? And the small guy is basically a neural network. Again, you multiply, and every step over here, these matrices, U, V, and W, these are learnable weight matrices, right? And it's shared across the entire sentence. Right? So these are the matrices that you're interested in learning when you are training this recurrent. Yeah. This is, again, what I just said. At each time step, we are looking at a function which takes an input and an old state and giving you the current cell state, right? Any questions so far? Okay, so basically, this is your entire sentence over here. What I just said was, look at how these weight matrices are of size xh, and your hidden states are of hh because they are going from here, they are multiplying from input x to hidden state h, and here it's basically a combination, multiplication of hidden state to a next hidden state, right? And then here you can think of it as going from the hidden state to the output y, right? So you have these three different matrices which are shared across all the time steps, and these are the three matrices that you are interested in learning. And of course, inside this, there are a bunch of different neural network layers which you have already covered, like simple MLPs, it could be CNNs, or it could be other kind of architectures that we'll see in a bit. So we are basically thinking of the entire sentence as these time points. We take the entire thing and then try to produce the output in the other language. And then finally, the ground truth labels, let's say, and you compute some kind of loss function. The loss function takes into account every time step over here, giving you L0 through Ln. And then you want to backgate through the entire thing to give your, to update your weights. This is very highly intuitive. If you really want to understand, you might have to like play with code and try to see where these things are backpropagating to. So a couple of things that you want to think of when you're trying to design these RNNs. The first is that it should handle variable length sequences. Basically, a sentence in English might not translate to exact number of words to another language, right? So you want to make sure that your RNN is able to take different length of sentences and translate into different length of sentences, right? It should be able to track long-term dependencies. What I mean by that is that if you have a really long sentence or like a paragraph, and then you want to translate that into another language, your neural network should be able to attend to different parts of the network. Like it should not forget information from the earlier sentence if it's trying to translate the current sentence, right? So that is basically long-term dependencies. Then it should also maintain information about the order. It's very important that you don't jumble up the order because a simple placement of comma can change the entire meaning of sentence in English. So it's really important to maintain that order. And then it should share parameters across the sequence. Basically, all these weight matrices are shared across the entire sequence, so that it attends to the entire input and output. Right? So these are the qualities that we look at when we want to think of an RNN. Any question? Cool. Now let's just try to. So that was a very high-level overview. Now let's zoom in and see what exactly is going on in every RNN component. And then after that, we'll see how we can think of notion of attention in RNNs, right? So as I said, this is your, let's say, one particular time step. You have your input vector, the X vector. You have your hidden state coming from the previous layers. This particular thing would give you two things. One is the next hidden state, right? Which I didn't tell you previously, but I'm just telling you now that it will give you hidden state for the next time step. And also it will give you an output for the current time step, right? So these are basically the two outputs that it is trying to give you at one particular time step. Hidden state from previous layer and input goes here. We get an output for the current time step, and we get hidden state for the next layer, right? So this is what is going on. Again, coming back to the bigger picture, we are trying to translate the sentence. We have an encoder, we have a decoder, and we have some context here, right? So this particular sentence, I'll assume that in the next slide, the first two words have already been processed. So I'll just zoom in and try to tell you what is going on at the last step, right? Or like one of the steps. So here what is going on is that we have the current word X student, right? It's vector representation, obviously. And then we have the hidden state coming from the previous processed layers. So hidden state, which encodes the information from these two words, right? So current word and the hidden state, which encodes the information from the previous two words, both of these get processed by a single RNN unit, and it gives you the next hidden state, right? And once you see that all these three words have been processed or encoded by this encoder into this hidden state number 3, now we want to decode all the information and finally use the decoder to produce the final sentence, right? And once the decoder plays its role, we will be able to convert the sentence into English, right? Again, just to repeat, this step is very important. We take the first two words, encode all that information into a hidden state. Then for this particular time step, we take this particular word, all their encoded information, and that RNN would give you this hidden state, which basically encodes everything, right? So that is a job of encoder, encode everything into some context, right? And now decoder would decode that into English, right? Yeah. 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 You can think, I mean, there are various ways to design it. Yeah, you can think of it as dynamic. So you can think of it as, let's say, you can think of it as actually a fixed vector, let's say 100 words. It's one representation, right? Like, don't quote me on this particular presentation, but you can think of it as like 100 words. And then if there are small sentences, you can just put some dummy variable in the rest of the representations, right? Basically, we put an end token to it. Yeah, there are both fixed representations and dynamic representation. Yeah, that's a good question. Yeah. Yeah, yeah. So that is out of scope for the talk. It will take some time to explain how those things are done in code. But as I was telling to last year, like, think of it as because you will be training it English to French. So when you're putting your training examples, right? So you have, let's say, 4 words in English, 3 words in French, and 4 words in English, right? So your input will be having, yeah, 3 words in French, right? And then I'll put in some kind of token or a dummy variable over there to make it the same length as my English sentence, right? But that is only one way to do it. There are dynamic ways to do it as well. Or that's the most vanilla way to do it. Yeah, so far so good. Like, what's the overall intuition behind RNNs, right? Okay, so before going on to next topic, can someone tell me what do you think the problems with these long-term architectures are? What are general problems that you can think of when training recurrent neural networks using backpropagation, or when thinking of having these long sequences as input and output in your RNNs? Like, what are some of the drawbacks? Yeah. Very good question. That's what transformers will take care of. Yeah. Yeah. Exactly. Yeah. Yeah. All those are good points. Yeah. Those are definitely problems with RNNs, which transformers take care of. Any other problems that you can think of without looking into the next slide? Yeah. Yeah. Okay, so we can like divide this into a couple of different ways of thinking about it. The first is, think of it as gradients, like the problem with gradients when you're computing forward passes and then your backward pass. So if your gradient at any particular time step when you're doing back propagation, if it's greater than 1, then when you keep on multiplying gradients at every layer, they will just keep on multiplying, and it might go, like, it might explode. You get a very large value of gradient, right? Which is something that you don't want, right? Because if it's a really long sentence or a paragraph and you keep on multiplying when you're doing back propagating, right? You're doing back propagation, and when the value is greater than 1 of a particular time step, they will just keep on multiplying exponentially, and the gradients will explode, right? So your minimas it might overshoot your local minima. So that's one problem when gradients are greater than 1. And when gradients are really small, somehow, what happens is that as you multiply a value less than 1 many times, it will tend to 0, right? So your gradients will vanish, right? So it has a problem of exploding gradients and a problem of vanishing gradients, right? So when you have exploding gradient case, what you can do is basically you can clip your gradient. You can say that if my gradient is becoming greater than 1.05, I'll just set it to 1.05, right? And if your values of your gradients are diminishing less than 1, what you can do is you can have a few different ways to take care of it. One of the way is using the ReLU activation function, which basically what it does is if your gradient is less than 0, it will set to 1, right? So that way you are near that range of 1. And that way your gradients won't go to 0, right? So these are like some problems, and as a couple of you already mentioned, it has no way of seeing or attending to components in the sentence which are very far away. So that's where transformers will come into picture. When we are translating sentences, it doesn't have, till now what I've shown you, it doesn't have any way to see the words that are coming next in the paragraph, right? And for translation, that is really important that you have the whole context of your paragraph to understand. So that is another problem. Again, transformers will take care of that. Another way to overcome these two problems is to just think of network architectures inside that RNN unit, which can take care of these problems explicitly. So you can design your neural network in such a way that it forgets useless information. It retains or captures, and only retains and captures information which is important to your current translation. And the way to do it is this. Basically, you can look at this offline. It's called LSTM block or a GRU block. So these are gated recurrent unit block or a long short-term memory block. So these are basically simple addition and multiplication and sigmoid and tanh functions that you can apply to your input and then produce the output and the next hidden state, which if you read these papers about these blocks, you'll understand why it is attending to a smaller region and trying to forget information which is not useful anymore. Right. So if you go back till here, when I was explaining this encoder-decoder part, so I told you here that it takes the entire input sentence, and the encoder would put all this information into this particular hidden state, right? And then then the decoder's job is to unravel this hidden state and produce the output, right? One problem over here is that this particular hidden state only captures information from its immediate previous input, right? So it only attends to the word student, right? Even though this particular hidden state has some context of things previously, at the current time step, it is only attending to what student is providing it, right? So again, the decoder is only looking at information coming from student, not the previous words explicitly, right? So we want to make some changes to this particular recurrent neural network so that it is able to overcome the problem of long-term dependency, and it remembers information from previous time steps as well. And it can make a decision of where to attend to in what part of the sentence, right? And then we'll think of how we can put attention mechanism into this encoder-decoder part of recurrent neural networks. So these are a couple of papers that you might want to look offline, which talks about how to put attention into RNNs, right? Again, this was done in natural language processing. And somehow, if you want to go into natural language processing, this is the group that you should start reading papers of. So again, this is what happened so far. We encoded all the information, input word, hidden state, output some over here, and then we have this hidden state, right? Sorry, where is that slide? Okay, so this decoding stage is only taking hidden state number 3, right? And now what I'm trying to propose is that I will send, instead of just hidden state number 3 coming out of student into decoder, I want to send all the previous hidden states as well, right? So that it has information from not only the immediate layer before the decoder, but all the layers before it, right? So just till now, what I've been telling you is that I'm only going to send hidden state 3 to the decoder, but now I'll just send all 3 hidden states from the previous time step as well, right? And the advantage of this is that now I can choose which hidden state to give more importance to, right? And that way, it will take care of long-term dependencies. So here we are right now. We have encoded. I'm sending all 3 hidden states, and decoder is also similar to the encoding stage, just like in your unit. And then it's gonna decode every time step into a different language. Right? So let's just think of one particular decoding stage, how it's going to decode, right? It's going to see hidden states from the previous layer. It's going to see some kind of input from this layer, and then it's going to decode that into a translated language. So remember that I'm going to send all the 3 hidden states, right? Represented here as 3 inputs. My output here would be the decoder. So right now I'm in my decoder, which receives hidden states from the encoder, and I want to get a new output that is the decoder output, right? The decoder hidden. So call from first, like I talked about how dot products are used to compute attention mechanisms, right? If you take dot product between 2 vectors, that basically means that I'm computing some kind of similarity and giving scores to every vector. So I have my 3 hidden states. I have some arbitrary scores that I'm going to assign to each hidden state, and then I'll do some kind of softmax operation, and it will basically give me how much I want to attend to H1 versus H2 versus H3. So I have some kind of mechanism to think about how much attention I want to give to these 3 hidden vectors, right? And then somehow I'll take a weighted combination of this and give the final output at the decoder time step, right? So visually, this is what is going on. Remember that we have this encoding stage, which spits out the 3 hidden vectors, H1, H2, H3. This whole thing is a decoding stage, right? This is the first time step of the decoder, which receives your 3 hidden states, the weighting for the 3 different hidden states, that is these scores. I'm going to multiply each of the hidden vectors with these scores to give some kind of attention to each of the hidden vectors, right? And I'm going to get some context vector from that weighting. Again, to give some context, hidden states multiply with some scoring function, and then I get some weighted combination of this hidden state, and I get some context vector C4, right? This is exactly what is going on here. After attending to the 3 different hidden vectors, I get my hidden state, my context vector here. And then using that context vector and the current input, I can get my hidden state for this particular decoder time step. This is exactly what is happening in the encoding stage as well. And I'm just telling you that it is the exact same architecture that I'm going to use for the decoder stage as well, right? This is nothing. It's just the same architecture throughout. It's just putting it into 2 different components, encoder and then decoder, right? This is exactly what was happening. This thing was exactly the same thing in the encoding stage as well. It's just that now I've collected all my hidden components from encoding in one go, and now I'm giving them weighted combinations, right? So yeah, again, input token, all this hidden information from this attention mechanism will give me this hidden state for the next state. And then I can combine some crazy combination of context vector and the current hidden state to give the output translation at this particular decoder output. So this would be the first letter, the first word I, right? Does it make sense, like intuitively, that it's the same thing that is happening in encoder, decoder? I'm just collecting all my hidden vectors together. I'm giving them some kind of attention weights so that it has context from everything that we have seen so far in the other language, right? That's about it. That's a takeaway message. It's fine if you don't get what a context vector is in one go, like, yeah. Right. So, and then you can do this for all the remaining words, and then you can get the corresponding translated output, right? So essentially what we did with this whole attention business was, I have my sentence in French, I have my sentence in English, And you can see how the different hidden states are playing role in decoding from French to English. So if you look at uh, this word "sui" in French, it basically translates to "am a," right? And for this particular translation, it looks at hidden state number 2 uh, when it is translating from French to English, right? So this confusion matrix is basically telling you what hidden state in from my encoder's output is essential in decoding it to English, right? Right. So from this word to this word, hidden state number 2 is essential, right? And it's leaning a bit towards hidden state 3 that it also saw something from hidden state 3 as well. Right? So two things, right? One, I don't know the grammar. uh, this is also a schematic, so don't again code on the schematic. Uh, but yeah, right. I don't have an answer. Like, why attending to this particular thing was the other thing. Also, student a lot too, right? Student is 1/3 of the total. Yeah. So like this guy, you're saying it should attend to student, right? Well, it attends to 2 and 3, right? Right? Yeah, the second point. Well, yeah, but I think like the A is attending to both 2 and 3, right? Attending more to 2 than 3, right? If you see vertically. Right? Yeah, I'll show you some examples after transformers, which shows us similar confusion matrix of how things are. But intuitively, it makes sense that A is actually on both sides, 2 and 3, right? Right. Any questions so far? So far, just to summarize, we looked at RNNs can be used for sequential modeling. We saw different ways of how one-to-one, many-to-one settings were there. We looked at many-to-many, in particular, sentence translation from French to English. We saw that it's similar architecture style of encoder and decoder. We talked about the input, the previous hidden state, and then these two things will give you the next hidden state and the corresponding output at a particular time step. Then we saw the problems with recurrent neural networks, both exploding and vanishing gradients, and the context problem with attention and how attention, simple attention can help in mitigating the problem of long sequences, right? Again, it's very intuitive talk. It's not going into the math in detail. So the nitty gritty is like how LSTM works or GRU works. It will take a lot of time to explain, right? So might want to read the paper. Hey, this paper is very important for your exam, so you might want to read this. uh, uh, so attention is all you need. This was, I think, 2017 paper, which basically is now bread and butter for every AI task. And again, I don't have to tell you what attention means, but just to illustrate it again, if you want to segment this particular Iron Man, yeah, no, yeah. Then how a neural network looks into segmentation of this particular foreground object is basically you have to attend to all the different pixels and voxels in your image, right? So the context is really important. We saw in text-to-text translation that with these long sequences, we really want to see what was behind us in a particular word, what is going to come in future as well. So left to right, top, bottom, you need to get that understanding. And transformer helps us doing that. That was one of the drawbacks with RNNs, that we couldn't see what was ahead of us, right? And transformers would take care of that mission as well. Right. So what we have seen so far in CNN or unit was that unit had one particular block at every layer, which comprised out of different activation functions, CNN layers, etc. Inside RNN unit, we also saw that one particular unit can compose of MLP, it can have LSTM blocks, it can have GRU blocks, different activation functions, right? And now with transformer, the building block of a transformer is this particular small unit over here. And you can call this basically a transformer unit, or you can call this as a attention unit, okay? And if we stack a bunch of these particular blocks on top of each other, stack them in an encoder decoder style to translate this, or to segment our images, or to register. So this is the main building block. Now we'll 30 minutes and try to understand what this building block is, helping us overcome the problem of attention. Right? So bear with me while I throw concepts at you. Just try to understand and hold this in your memory so that it makes sense. Why am I throwing these things at you? So an attention block is composed of three different things: a query, a key, and a value, right? You can think of as query as, so if you have studied databases in your computer science or electrical engineering training, think of query as when you go to put some kind of query, right? And then its algorithm will, at the back end, try to match it with different variables, right? Which has some key associated with it, right? And then with that particular, if it see, if the similarity is high, it would out, right? And when it sends you that particular output, it will the videos, aka the value particular, and then it will present that to you, right? So think of it in that way, that you are putting in a query, matches with some key, and then it will give you the value, or like it will rank the values in different, because there are many keys, so it will rank the different values as well. So query gets multiplied with key, or think of it as a dot product, right? Q times K. And then you normalize that with some constant. Take a softmax operation on top of it. And whatever output you get from this, you just multiply that with some value V, right? So this is what is going on inside an attention unit. That you take Q and K, dot product that, pass that through a softmax, and then multiply that with V. Right? So on the left, again, you have Q and K, which gets multiplied, aka dot product, which tells you some kind of similarity. You scale them basically, and then you go pass that through a softmax. V, right? This is what I told you. Right? MAT-mul is nothing but matrix multiplication. So you're multiplying Q times V, Q times K, normalizing them, passing that through softmax, and the output with V to get the final attention, right? So this is what is happening over here, right? You can now what Q, K, and V really means, right? So this is called one single self-attention or single block of attention. We'll come back to what is a multi-head attention later on. So far, it's good, right? I'm just telling you that these are variables and these are matrices which are getting multiplied in some fashion to compute some kind of dot product and similarity between each other. So we were translating our sentence from French to English. We did that with RNNs. Now we will throw that RNN away, and I will bring this transformer in, right? And RNN was built of that recurrent blocks of LSTMs and GRUs, right? And now transformer is built of these individual attention layers or attention blocks, right? So let's try to pick this apart. So transformer again can be thought of as encoder and decoder, right? Input goes to an encoder, then you want to decode it to get the output. Again, just as we saw in unit and RNNs, encoder can be different stacks of layers, and then decoder can again be different stack of layers, right? Each layer could comprise of CNNs, RNNs, or different kind of architectures. In this case, that attention unit inside all of these encoder blocks. So it's useful to think of it in this way so that you can relate to RNN and unit kind of architectures, right? So at the end of the day, everything is basically encoder decoder. So now let's zoom in and see what goes into this encoder architecture that makes it much more powerful than RNNs, right? So this is this one layer or one block of encoder over here. Basically, it takes some kind of input and it will give you some kind of output. Inside this particular encoder, we have that self-attention unit that I was talking about earlier. And then we have some other activation functions, other layers that you can throw in, right? So this is what is going on. We have our 3 words, and we want to translate that from French to English, right? So our input, if we go back here and look at this particular thing, our input and our first encoder block, it looks something like this, right? Where we have the 3 words in French, each of them represented by its corresponding vector embedding. Basically, the things that I was talking about, how a different word can be represented in a vector. So that is the input to the neural network. The first encoder block takes in some self-attention mechanism, translates that output into some, again, hidden variable, right, called Z1, Z2, Z3. And again, all of this goes into a feed-forward neural network, and then it prepares the output for the next encoder block, right? Now see that how in RNNs, we were doing it sequentially, X1 and then X2 and then X3, right? Here we are inputting all the words together in the network at one go, right? So that this particular block of code or architecture will be able to see what is behind or what is in front of the particular word, right? Does it make sense? Like we are putting everything together instead of putting in sequence one after another. So that's number one advantage of transformers, that information in this one particular go. Any questions? I look very confused. So here's what we are trying to achieve. It's all about context. So as Lasia pointed out, how a word in a sentence is able to attend to, or what it should look at, right? So if we want to kind of translate this word into any other language. The animal didn't cross the street because it was too tired. We want to understand what does it refer to, right? So in my input representation or whatever the attention mechanism is going to be, it should give more weighting to the animal phrase than to any other words in the input itself, right? Does it make sense, right? So when I'm translating the sentence into any other sentence, I'm gonna send this entire sentence to my neural network. It will give me some hidden representation, and that hidden representation for every word will be able to give some attention to the nearby words, right? So when I'm trying to encode this particular word it should be able to give more attention to the animal versus some other words in the sentence, right? And you can see it by the color of the shading of the attention. Makes sense, right? So again, we're trying to, let's say we pick up two words, thinking machines, right? And this is the input. We pass it through some self-attention thing. It gives you a hidden unit, Z1, Z2. Pass it through some feed-forward neural network, and then you get some output for the next encoding stage, right? And then in the next encoder as well, you have the same thing, right? But next time you have your input as R1, R2, and then it will produce another hidden state and another neural network and give you another output. Right? So how do you how do you come up with this attention mechanism? What does attention over here means? So now let's go back to the concept of query, key, and values that we talked about, right? So with every word in your input, you have its word embedding, X1, right? For that particular word, you also have some query Q1, you have some key K1, and you have some value V1, right? These are learnable parameters, right? These are something that you have to learn, right? So these vector embeddings are something that you have to learn, the neural network will learn. So it has parameters which you have to learn. And then you do the same thing for every word in an input sentence. So even for machines, you have your word embedding, which is your input. You have a corresponding key for this word, a corresponding query, and also a corresponding value for that word, right? So every word in your input sentence over here will carry this overhead as well, right? So far, so good, right? I'll come back to how these matrices are represented, right? Now, again, everything is about finding attention, which is nothing but finding similarity or closeness to each other, which, as we should know by now, is that it's just computing dot products with each other, right? So recall that I was telling you about this particular formula where Q times K divided by some constant, put it through some softmax, and then multiply by some V will give you some attention vector, right? So this is what this formula we are gonna use. So again, for these two words in the input, which I'm translating to some other language, I have these three things associated with every input of the word, of the sentence. And now I'll just try to compute attention between these two words, right? So just to zoom in for these vectors, thinking has this word embedding, query, key, and value, and machines also have the same thing, right? And now I'll try to find how much attention should I give to this pair of words. So I'm gonna first go back to my formula. I'm gonna multiply Q1 with K1 to give some output, divided by some normalizing factor. There are various ways to use this, define this normalizing factor, pass it through some softmax, multiply the softmax with the corresponding V value, and then I'll get some, that's it, right? And then I'll do the same thing, but this time, so the query is coming from thinking, right? And the first time when we did it, the key came from thinking as well. So it's a self-attention, like how much thinking should attend to thinking. And now I'm gonna see how much thinking should attend to machines. So the query will come from Q1, but the key will come from machines, right? And then again, I'll do the same thing. Divide by constant, softmax, multiply with its corresponding value V2, right? And then I'll just sum these V1 and V2 to get a corresponding sum Z1, right? And then I can do the same thing for machines as well. I can compute some kind of self-attention for machines by Q2 times K2, and then repeat the procedure for Q2 times K1, right? The other side. And then I can add it for V1 and V2 from the other side and get Z2, right? So going back to this picture, I have X1 and X2 as my input. And first Z1 basically tells you about how much thinking should attend to itself, and then how much thinking should attend to machine. So that information is encoding with Z1. And then in Z2, the information is how much machines should attend to itself, and then how much attention should machine pay to thinking, right? The other way as well. So basically what we are doing is for every word, we are incorporating some self-attention and also trying to think how much this word should attend to the nearby words, right? And we do that basically for all the words in our sequence. So the sentence can be really long, and we are doing it at one go for all this, right? Does it make sense? Yeah. So not really, right? So Q2, so when we're doing the other way, right? So the first term would be Q2 times K2, that is fine. And then the other way, it will be the query is gonna come from here, but the key is coming from here. So it will be different. It's not symmetric. Yeah, so it's I guess one again, it is this is schematic. The other thing is that context really matters, so we don't know what we are translating, right? I don't know how to say it. It's not necessary that it will be symmetric, because these are just two words. We don't know what's going on before and what's going on after. That might influence how much this word is going to influence this word, given that we have some information about the third word. Like, think of it as like a graph. Like, you don't know whether given a third variable, how much are they going to influence each other, right? If you have studied probabilistic graphical models, that's always the case, that you don't know how much a third variable can influence how much these two are interacting, right? Because if you're looking from, let's say, from the right side, a third variable might influence these two words in some different way, while from the left side, a third variable might influence these two in a different way.
Is there any like physical relationship with the curious speed of values, or it's just like a set of three vectors, like tune or everything?
Exactly. So, yeah. Any questions or comments? Yeah. How do I get the softmax? Just a softmax function, and like oh, so it's so when we are so if you see this, right, so it's input from all the different values, you mean? Yeah, from the entire. So it's gonna be from 14 and from 12, right? From all the, from Q1 times Kn, where n goes from 1 to. Does it make sense? So just for this particular step, you can see, right? The softmax is coming from this softmax and this softmax is coming from these inputs, which are basically Q1 times K1, Q1 times K2, Q1 times K3, and so on. So those are the values which are being used to get the softmax. Yeah, yeah. So this is a vector and then this is a vector. Right? I mean, these are technically matrices because, but for one attention, it's we're running out of time, but this should be enough for your midterm. Now just so till now, does it make sense what we are trying to do? We are just trying to learn Q, K, and V. These are just vectors that are trying to pose information from different parts of the of the of the image or the sentence.
I have a question related to this. This is my understanding, and I could be wrong, but I think basically the Q and K, the frequencies are a way of learning a matrix, because what you essentially want to learn is a matrix that relates all the inputs together.
Yeah.
It's the matrix that attends, you have 10 inputs, and you want to build like a 10 by 10 matrix of how much each input inputs each other. And that's 100 values. That's too much to learn. And it could be different for different problems, right? You have a sentence of 20 words, now you have 20 by 20. So this Q and K is like a way of, through an outer product that constructing a matrix, a weight matrix. And then you essentially create this weight matrix, you normalize it so that all the weights add up to 1. That's what the softmax is doing. And then the value is just like that x1, diluted into some other representation.
Yeah.
And then you weight that value by by the attention matrix. So like the word thinking, you get contribution from all the other words weighted by the attention. It's just like a trick to create an attention matrix, regardless of the size of it.
Yeah. Yeah. So as Paul said, you can think, I was gonna talk about this in matrix representation next, but yeah, every word embedding have a diluted form as value, and its corresponding query and key when dot producted with the other words will give you some kind of relation between the two words. So this is for one word at a time, but this is deep learning, so you can stack everything together, right? All your input X, all the inputs in that particular sentence, so thinking, machines, whatever, you can stack them together, and then you can have a corresponding query matrix as well, query weight matrix as well. Again, stack them together. You can do that for keys and values as well to get your final matrices, right? And then you just Q, K, and V, you apply everything on these matrices, right? So that was just one sentence or 2 words at a time. Now this is your entire chunk at a time, right? So this is what is going on. We have these matrices, dot product, scaling, softmax, multiply by the value to give hidden representation C. Right. Oh boy. Okay. So 2 main concepts. Okay, I won't have. Okay, I'll finish this explanation of transformers, and then I had some papers which discuss how transformers are used in medical imaging. So I was not gonna cover them anyway, but they're in the slide, so you can look up how units are now from you saw unit, and then you saw any unit, and then there is something which is transformers for any unit. So till now we saw this concept of single attention, right? Where at one particular time you were getting this particular matrix Z for a set of inputs, right? Now, multi-head attention is basically you're repeating this procedure n times, right? So for every word, instead of now having one value of Q, one value of V, and one value of K, you can have n number of Qs, Ks, and V associated with one particular word. Basically, think of this as attention, multiple attentions, right? So it's called multi-head attention, where instead of just having a single vector of Q, V, and K for one word, I'm gonna have n number of Q, K, and Vs, which are all learnable, just to give more context and more information to the network. So it becomes more powerful, right? So again, I have my input X, right? And till now, you just saw one particular component, right? Which learned on Q, K, and V. Now I'll have another Q, K, and V, and then another set of Q, K, and V for the same word, and just basically repeat this 7 times, 8 times, 9 times, what you have. So the whole attention business, you just repeat that different number of times. So learn more parameters in your network. That's about it. Think of it as stacking different layers in your network. You're just stacking different attention heads together. So we saw this particular output, and then I'll just repeat this thing n number of times using different values of Q, V, and K, and I'll just concatenate them, add them to get one final representation. It is, think of it just ensemble of different Q, K, V combinations. Yeah. Nothing fancy, just, so this is just multi-head attention where you're repeating the blocks n number of times. Yeah, and again, you can represent everything in a matrix form to get first input. You have first sets of Q, K, V, you get Z naught by doing that whole attention thing. I have another set of Q, K, V. Again, these are learnable vectors and matrices. I have Z1 and so on till Zn. Add them up together, concatenate them, softmax them to have a fancy representation called Z. Right? Yeah, one final thing. One way, so far what we did was we had this input, and then we directly took this input and threw this into an encoded representation, right? But it's all fine. I've taken my input information, put that into encoder. And I also said that there is enough attention power over here to be able to attend to parts of the network, of the sentence, right? But someone had asked me that how can it know where in the sentence basically I'm trying to look for the information, right? Which word comes before which word when I'm trying to translate it from French to English, right? So that is where something called position encoding can be helpful, right? That when I'm trying to translate from English to, let's say, Hindi, where in English, the articles come somewhere in the middle of the sentence, but in Hindi, they come towards the end of the sentence. So how can I tell my network that the position of these articles is important when you're translating the sentence, right? So I can put some extra information along with this input representation called position encoding, which not only tells you the current word embedding, but it will tell you where in my sentence is this particular word occurring with respect to this previous word or the next word, right? It's basically very simple. Like it's just giving me information about the position of the image of the sentence. And we just basically concatenate these two information together, or we can just sum them together and just send it as we were doing before to this encoder block, right? So there are many different ways of thinking about this position encoding. Can someone like try to come up with what kind of information can I give which encodes the position of the different words? Anyone? So it could be as simple as like 1, 2, 3, 4, right? I can just tell my network that this is this particular word. I'm gonna assign it a one hot vector, which tells me that it is at position 1. This particular word will be at position 2. This particular word will be at position 3, and so on, right? But that is a very vanilla way to do it. But we want something which is learnable, right? So we can just use something as simple as a sign function, right? Which has some temporal degree to it, so that it tells me where in the network this particular word is occurring. So I can take the sign function. This is a discretized sign function. And at every input, I can put one of this particular block of information, concatenate this with the input information, and then send it to the encoder. Right? So you might want to read this offline in the paper. What is sinusoidal encoding and how position encoding helps in attention networks. Right? So in like one sentence, you can have your input sentence, and you can have a simple sign function or 1D sign function, which tells you, which gives you a temporal aspect, right? And then you can have each temporal encoding of the sign function concatenated with corresponding input and send that to the network, right? So it could be any function of your choice, which has some temporal information that gives you some kind of position. So yeah, I think I should stop here. We didn't get to talk about how decoders work in attention, or like transformers. We didn't get a chance to talk about how these things can be used for images. And then I also wanted to cover some code and talk about how transformers are used in image segmentation. Maybe catch-up class. I would say I would revise a few things again. I think last 15 minutes were a bit rushed. So like 30 minutes. Yeah, well, I feel like yeah, maybe on Monday I can like talk properly about what position encoding is and talk about decoder. I mean, I don't know. Thanks.